Hey guys, we're wrapping up chapter 1 with section 1.5, infinite limits. Today we're going to talk about a concept that we've looked at a couple times this chapter, so don't be surprised if this looks familiar to you. Now we're just kind of looking at it more formally. So what is an infinite limit? An infinite limit is exactly what it sounds like. It's going to be a limit in which the function, which we'll call f of x, increases or the opposite, so decreases. So we're looking at, it's a limit in which f of x increases or decreases without bound. What does that mean? As x approaches c. So let's see what this means. Without bound. That sounds kind of fancy. So what am I talking about when I say infinite limits? Well, here's one. This is going to increase without bound, increase without bound. It's going to level off here. Another one could be this graph. This one increases without bound, and the other side decreases without bound. So in both cases, if we look at, this happens to be 0 in both cases, but as we approach x from the left, positive infinity, right, positive infinity. So maybe this without bound thing is referring to infinity, which totally makes sense since it's called infinite limits. Okay, moving on. Does the function 1 over x have any vertical asymptotes? Well, this is a function like the one I just drew above. So 1 over x looks like this. Does this have any vertical asymptotes? Think back to what you know from pre-calc and just answer. Sure. We could say there's a vertical asymptote. Yes, it does, at x equals 0. So we're going to try to tie these together. So what does that mean then? What's happening as we get closer to 0? Why is there a vertical asymptote? Like we can see by looking at it there is, but how can we use calculus to show this? So on your table, which we've looked at before, I'll go over it with you in a second. Let's start off by looking at 1, 2, 3, 4, 5. So let's go 1, 2, 3, 4, 5. Let's put a 0 here. We're going to creep up on this again. We're going to get kind of far away from 0. We're going to go to -1. Then we're going to go to -0.1, -0.00. Oops, too many O's. -0.01, and then -0.001. And then now on the right, we're going to creep up. Remember, we started day 1 of this chapter looking at tables. We're going to start here and we're going to get closer. That's a 1 until we're right up on it. Now, actually, I don't even want to get the calculator for this. I think we can figure this out. We know at 0, if I sub a 0 into this function, I'm going to get 1 over x. We know that does not exist, so we're going to go ahead and write this here. I'm going to look at my integers. If I sub a -1 in, I'm going to get -1. If I sub a 1 in, I'm going to get +1. Now, think about what this is. What's happening here. I have 1 over x as my function, right? But if I replace x with what they tell me to, so in the first case, I'm looking right here, it's 1/10. So I'm going to go ahead and sub in a 1/10. This will actually be quicker than the calculator. Remember, when you divide by a fraction, you multiply by the reciprocal. So this is 10, which would make this 100 and 1,000. And we're not even actually that close, right? We could get a lot closer. So what do you notice about the numbers as you move in from the right? They're getting huge, right? And if we put like a whole bunch of O's in one, we're going to get an even bigger number. Look up at the graph. As we move in from the right, we're getting so much bigger, which matches our data set. On the left, were you going to use the same idea? And now this is going to be -10, -100, and -1,000. So as I move in from the left, let's look at our graph. I'm coming in from the left. Oh, now look, it's going down without bound. So do you get it's approaching negative big numbers? And that's what's happening there. Okay, so looking at the question, as the denominator approaches 0, what happens to the value of the fraction? The value of the fraction gets large, either in the positive or negative direction. Examine the right and left-hand limits. Good, this will give us a chance to practice these. So the limit, as x approaches 0 from the left, of 1 over x, and then we're going to look at the limit as x approaches 0 from the right of 1 over x. Let's write 1 over x in there. Okay, so from the left, what did we see? We could look at the graph. Sorry, this is moving. We could look at the graph and see it's going to negative infinity. We could look at the data to see it's going to negative infinity. So we know that this answer is negative infinity. On the right, if we look from the right-hand side, the numbers are also getting big. The graph numbers are also getting big. So this is an awesome way to end the chapter because we're tying in stuff from day one. Okay, so we can see with vertical asymptotes, look at what happened. We got answers for the limits as we approached the vertical asymptote that were either positive or negative infinity. Okay, going on to example 2. So that seems to be the big idea today. On the first one, I gave you a function. B, we're going to use the graph. So I'm asking you the limit as x approaches negative 2 from the left and the right. First of all, if you try subbing negative 2 in, do you guys see you get 1 over 0, which is so not helpful, right? But that's okay. They asked us for individual left and right also. So we're approaching negative 2 from the left, and then we're approaching negative 2 from the right. When we did this before, I said, okay, even though it's approaching from the left, let's try subbing a negative 2 in. Because remember, if the limit exists at negative 2, then the left and the right have to be the same. We tried negative 2 and got 1 over 0. So now this is the kind of problem. We don't have a graph. We really just have to think about it. If here's negative 2 on the number line, and if I'm right to the left of it, because it said negative 2 from the left, I'm right here. Now, we can't even identify that number. It has so many zeros. It would be like negative 2.01, right, with a whole bunch of zeros. But let's just pretend. So this is the part that really isn't true work. This is me just explaining to you what you should be thinking. So you should be thinking negative 2 point, and I really want to write a million zeros, but we don't have time. So that when I sub it in, I don't even know if that's the same amount. I'm going to get 1 over a super teeny tiny negative number. 1 over a tiny number is a huge number with a negative, making it negative infinity. On the next one, so let me go ahead and circle this because there's some thinking stuff. Here's our question, okay? On the next one now, we are at negative 2 to the right of it. We're right here. Now we're at negative 1.9999999, a whole bunch of those. So we're thinking of that number. So I have 1 over negative 1.99999 plus 2, which is 1 over a super tiny positive number, which gives me infinity. And there's that answer. So again, we've looked at some of these similar. Now, what does that mean now? If we get a negative infinity or a positive infinity, we haven't really seen anything definitive yet, but we saw up above that when we got a positive or negative infinity for our limit, that the number it approached became our asymptote. So let's keep an eye out for that. Let's see if we can figure something out. Look at the graph of this. If I go to graph this, the graph actually has a vertical asymptote at what value, guys? Try to think about it. It has a negative 2, and you could just graph this on your calculator if you wanted. And then when you go to graph it, it looks like this, and this piece goes like this. So let's make sure if everything we're saying makes sense. We thought because we got a negative infinity or a positive infinity as our answer, that there was going to be a vertical asymptote here. If we approach negative 2 from the right, we get positive infinity, which is what this says. If we approach negative 2 from the left, we get negative infinity, which is what that says. So everything seems to be lining up. Let's go to the next one. Now here I gave you a graph. We're just going to practice using the graph. So let's approach negative 2 from the left. And let's approach, these arrows are kind of hard to draw on this, negative 2 from the right. Okay, negative 2 from the left. Here's negative 2. If I fly in from the left, I go to negative infinity. If I fly in from the right, here's negative 2. I go to positive infinity. Look what's happening again, guys. We have a vertical asymptote at negative 2. What did we get as our answers? Positive and negative infinity. Interesting. Okay, let's see what the next page tells us. Hey, one question. What if I asked you for the limit as x approaches negative 2 for this problem? Find the limit as x approaches negative 2. You wouldn't have to do any work. Couldn't you see that because the left and the right don't match up, the limit doesn't exist? Okay, just a little review. Let's go on. Okay, I see a box, so this might be making a conclusion based on all this work we've been doing. This says similar to a jump discontinuity. Do you guys remember what that is? A jump discontinuity looks like this. The limit will always fail to exist at a vertical asymptote. Do you remember the limit failed to exist at this jump right here? Because the left and the right wasn't the same. They're saying the limit will also always fail to exist at a vertical, but for a very different reason. Look at what your choices are. You either go down to negative infinity or go up forever to infinity, neither of which is a limit, right? So when we get infinity or negative infinity as an answer, remember I was having you write that, but the book might write DNE, just to recap on some old stuff. Okay, non-removable infinite discontinuity is called a vertical asymptote. Look at what we're getting, negative infinity, positive, and if it's at these C values, then those C values are your vertical asymptotes. Do you guys remember what non-removable meant? Okay, we looked back at that a couple days ago at the notes. It means it wouldn't factor out, and I'll explain that as we go on, just to refresh your memory if you don't remember. Okay, so what we thought we saw on the last page is every time that we got an infinity as our answer, it looked like this gave us a vertical asymptote, and now we know we're right. This is just asking for vertical asymptotes of the function. If you were to take the limit, look up above here, at where we thought there would be a vertical asymptote, we would get plus or minus infinity. Here we're just going to kind of work through these a little quicker. Vertical asymptote is the bottom ever equal to 0. Look at this bottom. Do you guys see that this could never be equal to 0? Because we would want this to be -4, and it never can because it's squared. So find the vertical asymptotes. We'll just say, no thanks, there are none. Denominator never is 0. What about this next one? Isn't secant 1 over cosine? Okay, there's not a cosine pi over x up top to factor away. That was the removable kind. So this looks non-removable, which will make it a vertical asymptote. So let's look at this one. When is the bottom equal to 0? Let's draw a unit circle real quick. When is cosine 0? Cosine is 0 right here at pi over 2 and at 3 pi over 2. Okay, but they have cosine pi x. So we're saying when is cosine pi x equal to 0? Well, that's when this thing right here is either pi over 2 or when this thing inside is 3 pi over 2. So that would make x to be 1/2 or 3/2. Now they don't have a domain restriction here, so you're going to keep going around and around and around this circle, so these numbers are going to keep going on. Now if you remember before in your book how we've always written answers like this, because it's not just 1/2 and 3/2, the answers actually keep going, 5/2, 7/2, and on. A quick way to write this is to make an equation. So we'll say actually x is going to be, and how I do this that I find to be pretty quick, is I'm going to take this first number in this sequence here, and I'm going to go ahead and make that, think of like y equals mx plus b. That's going to be my b. Now what do I add as I go here? Let me draw it this way, from 1/2 to 3/2. What do you add? Do you see that you add a 1? So that's kind of like your slope. So it would be 1 times n, but remember, we don't need to write a 1 there. I just did that to show it. Now, let me show you why this makes sense. Well, let's go on and finish this first, actually. And then you would say n is any integer. What this does is this gives the idea of 1/2, 3/2, 5/2. N is any integer. Let n be 0. If n is 0, we get 1/2, which is right here. If n is 1, what's 1 plus 0.5? 1.5, which is here. Let n be 2. 2 plus 0.5 is 2.5, and you can see why that works. Next one. Okay, we're finding vertical asymptotes. So we have this function here. We want to see when the bottom is 0. How about we factor the bottom? Since we're factoring the bottom, let's go ahead and factor the top. Oh, this is a factoring by grouping. Look at the first two. You can take out an x squared and you're left with an x plus 2. The next part already has an x plus 2, so I'm just going to write a 1 there. Now on the top, I have x plus 2, x minus 2. On the bottom, now I have actually two terms. I have this first term and the second term. They both have an x plus 2, so I'm going to take an x plus 2 out. What's left is an x squared plus 1. So we looked at removable discontinuity before, and it's when it factored away. Okay, so what's factoring away here? What's not factoring away? Right here. Now, can that ever be 0? It can't, because this first piece would have to be a -1, and it can't because it's squared. It's just like the case that we saw over here in A. So this is an odd case too, again, that we have none. I wanted you to see here that even though we have a value in the denominator, like -2, you have to decide, is that a removable discontinuity or is it going to be a non-removable, and in this case, a vertical asymptote? Because it factored away, we removed it, and it's a whole. Okay, going on to these. Example 4, does this have a vertical asymptote or removable discontinuity? So this is what we're looking at here. Oh, at x equals -1. Okay, let's factor this. We're going to get, see if you can factor faster, -7 and +1 all over a +1. Okay, so let's look at this. To know if it does or doesn't, we have to see what factors. What is the issue here? In the bottom, we don't want this bottom. We can't let x be -1. Okay, x cannot be -1. So we have some kind of issue. Do you see it? We also have x plus 1 up here. So because these factor and cancel, we removed it. So what's a quick way to call this? It's a quick way to think about it. It's a removable discontinuity. Okay, we could say there is a removable discontinuity at x equals -1. The graph, guys, just to recap with you how to graph these, we know at -1 there's an issue. So at -1 we have to have a whole. Remember, because it removed, it's going to be a whole. Now this function and this function agree at all but one point. They agree at all but -1. So what we really are going to do is graph this line, and there's going to be a whole at -1. Okay, so this is going to, look, it has a y-intercept of -7. This is going to be a pretty quick sketch. At -1, -8 is the whole. And then you also hit at 7 up here. So it's going to do something like this. And sorry, I'm out of space here, but you know that that continues on. To be a vertical asymptote, so let me tie this into, a lot of this was review. Let's tie it into what we're saying today. Our claim today is to be a vertical asymptote, the limit has to equal, I'm abbreviating there, has to equal plus or minus infinity. Remember up here, we said that if the limit of the thing you're approaching is plus or minus infinity, then we have a vertical asymptote. Well, what's this limit? Didn't we cancel? And then we could do direct sub by replacing -1 into here, and you get -8, and that's what our picture shows also. Oop, not infinity, -8. Let's clean that up. I'm used to infinity on this page. Look at the picture over here. From the left was -8, from the right was -8. Okay, you really don't have to like do all of this looking at this problem. We saw right away that because the -1 went away, it was removable. Okay, but I did want to tie it into the new concept. Okay, so for the most part, done with the idea. Now here's the extra examples to help you through your homework. Okay, these are just some trickier limits. Let's look at the first one. If they ask you to approach 1 from the right, remember, if 1 works, then you're good. Because if the limit as x approaches 1 exists, then of course the left and the right do. However, you try subbing a 1 in and you get 3 over 0. Not a good answer. That's not going to be helpful. So normally when you have a number over 0, it's going to give you a vertical asymptote. So we'll either get plus or minus infinity as our answer. So direct sub is what I always want you to try first. And we got 3 over 0, so it looks like it's a vertical asymptote. Remember, if we're approaching 1 from the right, what number is really just to the right of 1? Isn't it 1.0001? So if you sub that in, again, not knowing if the zeros match up, we're just thinking through this, you're going to get 3.001 over a negative super tiny number. Now, in the grand scheme of things, this 3 up top is really irrelevant, right? 3 compared to a number so small we can't even count it is still going to give us negative infinity. Okay, looking at the graph, again, not needed. I just put the graphs here to help you to see what's happening. Here's one right here. You know what, let me fix that. I'm gonna make it dashed. It's actually a vertical asymptote. How do we know it's a vertical asymptote? Because we got infinity as our answer at that limit. Okay, this sketch. So again, I'm just sketching a quick graph. I get this is not perfect. 0 looks like 2. We're going to get something like this. Can you guys see as we approach 1 from the right? Here's 1, approach from the right, and it goes down to negative infinity. Plus or minus infinity as our answer means vertical asymptote. Okay, going on. This one, 4 from the left. I always want you to try direct sub first. Remember, who cares that it's 4 from the left? If 4 works, then the left and the right have to be the same. So direct sub with x equals 4 gives you 4 squared over 4 squared plus 16. Isn't that a half? Oh, awesome, we're done. No more thinking about these different numbers. We're good there. This graph actually is pretty flat. It's hard with this pen width, but it's doing something like that. So you can see there's no breaks. Look back up here at the domain. Look at the bottom. There's no way that can ever be 0 because there's no way that this squared number can ever be negative 16. So 4 was good. It's in the domain. We subbed it in and got 1/2. If you look over here at 4, 1, 2, 3, 4, sure, that's about 1/2. I know it's a really rough sketch. Next one. 0 from the left. Who cares that it's from the left? Let's try 0. Oh, that's not good news, right? If we try direct sub and sub 0 in, we're going to get 0 minus 1 over 0. This thing down here isn't good. You can't have a 0 on the bottom. So now we have to play this whole thinking game. So what is right to the left of 0? It's a negative super small number. So we're going to have a negative super small number squared minus 1 over a negative super small number. Okay, first part essentially is 0. Negative and a negative is a positive. So let me show you what I'm talking about. This negative and this negative gives you a positive. And what's 1 over tiny? 1 over super tiny is super big. What's super big called? Infinity. So we get infinity. Remember, again, I want to stress this part here isn't like proper work, right? This is a way for us to think through this. If you get infinity as an answer, doesn't that mean that this is a vertical asymptote? That's what we're learning about today. If we go ahead and graph this, that means 0 is a vertical asymptote. Your graph is going to look something like this. If you want to do it on your calculator to see it, go for it. And then I think you get something over here. Let's see, again, I'm just doing this to illustrate to you what it looks like. 0 from the left, here's 0, vertical asymptote because we got infinity as an answer. Fly in from the left. Do you guys see you get infinity? Okay, next one. Guys, what do you always try first with limits? Direct sub with x equals 3 yields a 3 minus 2. Oh, look at this is good. We get 1/9 and we can call it a day here. Okay, again, another problem to help you on your homework and stuff. We did the concepts above. These extra problems that I have down here, I would love for you to try them on your own. Like maybe try A, listen to the video, check it. B, listen to the video and check it. It's a great way to assess where you're at. Okay, we want to approach negative 1/2 from the right. So look at what the problem is. It's a piecewise. You know, I like giving you a lot of those to practice with. They're saying this function is continuous except when x equals negative 1/2. So what's going on at negative 1/2? Well, they're asking us to find the limit of negative half from the right. So let's do that. The limit as x equals negative half from the right. Shouldn't we try direct sub first? We probably should, but how about we factor this first? It just looks like messy to sub in a half everywhere. So let's go ahead and factor this. We are going to get x plus 3, x minus 2. You guys try to do the bottom on your own if you didn't pause it. 2x plus 1 and x minus 2. Okay. Again, I didn't sub the negative half in yet. I don't feel like dealing with it quite yet with all those numbers squared and such. I do notice that these cancel. What does that mean, guys? If you have them factored and then cancel, that means when x is 2, we are going to have what on the graph? A hole. Is it removable or non? Removable. Okay, now that we have something a little easier to work with, let's try direct sub now. I'm going to get, remember it said negative half from the right, but if I can plug in a negative half, then that's going to be okay. So I'm going to get negative half plus 3 over 2 times negative a half plus 1, which is going to give me 5 halves over, you know what, I think I wrote the bottom wrong. Let me fix that real quick. I just think the parentheses were in the wrong spot. It's 2 times negative a half plus 1. And oh shoot, that's a 0. Okay, so a number over 0 is most likely your vertical asymptote, but how do we know if we get a vertical asymptote? Isn't it if we get plus or minus infinity as our answer? Okay, so even though it was coming from the right, the negative half, we tried negative half hoping it would work. It did not, so now we really have to think about it. So our thought process, well, what is right? What is right to the right of negative half? If you're on a number line, let's see, I'll use some space here. If here's negative 0.5, yeah, let's use decimals. You're at negative 0.5. Right to the right of it is right here. Isn't that negative 4.99999? So that's what we're thinking of. We're thinking of negative 0.4999999. So that's going to give us, remember this is not proper math per se, it's our way to think through it. And then we have 2 times negative 0.4999999 plus 1. The top is going to give us approximately 2.501. Again, I'm not counting zeros to make sure everything matches up. We're just thinking through this. The bottom, this is going to be a negative number just shy of 1. Plus 1 is going to be a super small number. What's 2.5 over teeny tiny? 2.5 becomes irrelevant. So something over a really small number is going to be positive infinity. Let's try the circle thing, see if this works again. Oh, awesome. Okay, looking good. Okay, next one. Limit as x approaches 1. Let's go up to the problem. Okay, limit as x approaches 1. Oh, you know, one other thing I want to point out since we're looking at this kind of piecewise, remember when they just have x equals 2. So this is just the point 2k. Remember, limits don't care about existence. We care about what's going on around it. So that's why on A, I took just the first part of the piecewise. I don't care about the point. Okay, I just wanted to remind you of that. Limit as x approaches 1 now. Guys, what are we always going to try first? You know it's direct sub at this point. 1 is pretty easy to sub in. Let's hope we don't get zeros in the bottom. We're going to get 1 plus 1 minus 6. We're going to get 2 minus 3 minus 2. I love how this is looking. We're going to get, is that a negative 4 over 2 over a negative 3, giving us 4/3. Done. So this is a reminder of things don't have to be difficult. Okay, we subbed 1 in. We didn't get anything crazy and we're good. Okay, what is the value of k? Now, if they tell you that f is continuous except at negative half, and k involves this point here, then isn't the limit of f equal to, as x approaches k, equal, I'm sorry, as x approaches 2. Let me write it out. Okay, k involves the point. So what we're going to say is because we know the function's continuous at 2, we're going to say the limit as x approaches 2 of the function. What does continuity mean, guys? It means f of 2. We know f of 2 is k. They already told us that. Now, as we go to deal with this, we're going to use the factors. We already factored it in a, so let's not do too much thinking, and let's just use the factors we found, right? Why do more work? Oh, shoot, now we have an issue. They're saying, hopefully we can sub 2 in, but we have a 0. But what's the good news? These cancel. Okay, so now we're going to get the limit as x approaches 2 of x plus 3 over 2x plus 1. Remember, the reason we're setting this up, just to go back, is they told us the function is continuous, so, except here. But it is continuous at 2. So that means this output has to equal the limit. Now let's try direct sub. It should work. We're going to get 5 over 5. K is 1. And we are done. Awesome, guys. See you later.